let's continue into 1.6 and do some examples with integration. So here's our standard, our basic integral formulas. But we'll have to manipulate the integrand to match this form. So this is really our first time we're kind of looking at what you'd think of as tables. You look up tables of integrals. And so once we have this right form, then we'll be able to say what the integral equals. So let's take a look at this one. This one is a definite integral, 0 to 1/4. And so what we want to do is rewrite or think of this as the integral from 0 to 1/4 of 1 over the square root of 1 minus, and that's 2x squared dx. And so this will be our u substitution. So we can then say let u equal 2x. So du is 2 dx. And solve for the dx. So du over 2 equals dx. And that's what we substitute for. So this equals the integral from 0 to 1/4. And so you'll need a half on the outside. That's where this is coming from, right here. And then you get 1 over the square root of 1 minus u squared du. And so now we apply our integral formula, and that's going to be a half sine inverse of u evaluated from, and this is where we want to say this is x equals 0 to x equals 1/4. And then let's go ahead and substitute back for our u, is what we normally like to do. So here's u, and we'll substitute back for that, and we'll have all the same variables. So that's equal to a half sine inverse of 2x, and then now this is, you don't have to put in your indication of variable because it's just, it's the same x, so you say 0 to 1/4. And then we evaluate that. So that's equals 1/2 times sine inverse of a half, right, because you're putting 1/4, minus sine inverse of 0. And so we have to evaluate sine inverse of 0 and sine inverse of a half. So sine inverse of 0 is 0 because sine 0 is 0. So that one's easy to do. So this one just goes to 0. Okay, so that goes to 0. And so sine inverse of a half, we can go back and evaluate that. Or did we already do that one? Well, basically, so what value of sine is a half? And that's pretty easy on this one because it's this guy. Or no, I'm sorry, xy. So this one, so pi sixth. If it's in the first if it is in the first quadrant, it's always a lot easier. Oops, not too far. Okay. So we get this to be 1/2 times pi sixth, which is equal to pi 12ths. Okay, next one. Let's bring this up a little bit. Oops. All right, so next example, evaluate this one. You can see right away this looks kind of like a tangent right here, but this has to be a 1. So we're going to have to rearrange this quite a bit. So let's see how you do that. So you kind of, it's almost like if you can, you force it to happen. So we're going to say this equals, we're going to rewrite this as 1, oops, I didn't write that very well, did I? So we're going to rewrite this and we're going to say this equals 1 over, and then this is a squared, and then this is x squared over a squared plus 1. So now I have the something squared plus 1 dx, and I will factor out the 1 over a squared, and this is just an indefinite integral. So now to get it in the correct form, this should be 1 over and then x squared over a quantity squared. So now that's my u substitution plus 1. And so now I can say let u be my x over a so that my du is 1 over a dx. And so you get a du is equal to my dx. And so one of those a values will reduce and simplify. So you have a squared there and an a here when you substitute. So one of them is going to reduce. So that equals 1 over a times the integral of 1 over u squared plus 1. So that's now exactly the correct form, du. And so that's 1 over a tan inverse of u plus c. And you will see that that is the integral formula. So if you have this form, this is actually the formula that you will be given or use. So actually from here to here. So, oh, and then substitute back. I almost forgot that. So you want to say 1 over a, and then that is tan inverse of, and then what was u? That was x over a plus c. And so that is actually the integral formula we use, is really that form. So move this down to here. We'll do that one next. And so your integral formula looks like this. It's actually 1 over x squared plus a squared dx is equal to 1 over a tan inverse of x over a plus c. So that's an integral formula that you will be able to use, look up, and evaluate. Okay, so let's do one more of integration. That's usually the more difficult stuff, is integration, then derivatives. Okay, so this one, similar form as above, but it's going to take some more work to simplify this thing. So what we can do is find that, so you can write this as integral, and then say this is x over, and then this will be x squared, quantity squared, and then plus 3 squared dx. So it's close to the form we want. If we do a u substitution, so we want to let u, let me come back over here. So if we let u equal x squared, then du is 2x dx. And so du over 2 is equal to my x dx. So when I substitute in, I get the integral of 1/2 and then that'll be 1 over u squared plus 3 squared du, where a is equal to 3 in that formula above, right? So in this formula, that's what you get. So this is equal to 1/2, and then apply the formula, times 1/3 tan inverse of u over 3 plus c. But see, that was for u, so what was u? U is x squared, so that's going to be 1, we'll evaluate that, 1/6 tan inverse of x squared over 3 plus c. So this was, you had to simplify a little bit first with a u substitution to get the correct form of the formula above that we can apply. So this half is just tagging along. That's not part of the formula. But this 1 over a, this 1/3 is. And then you substitute back for your u. Okay. That wraps up 1.6. And next, the last section we'll cover in Chapter 7 is on what's called hyperbolic functions. And we'll get to that next.